Have you ever found yourself wondering if light is a wave or a particle? Or perhaps, is it both? This question has long puzzled scientists and sparked a host of experiments and theories. So, let's begin our journey into the enigma of light and particles. On one hand, light behaves like a wave, rippling through space, much like waves on a pond. This wave theory of light, supported by experiments like Thomas Young's double-slit experiment in the early 19th century, explains phenomena like interference and diffraction. However, there's another side to this story. Light also behaves like a particle. This view, known as the particle theory of light or the photon theory, was bolstered by experiments like Arthur Compton's scattering experiment in the 1920s. Compton showed that photons, particles of light, carry momentum and can scatter off electrons, much like billiard balls colliding on a pool table. Now, meet the photon, the star of our particle theory. Photons are discrete energy packets or quanta of light. Albert Einstein, in his explanation of the photoelectric effect, introduced the concept of light consisting of these particles of energy. Each photon carries a specific amount of energy, directly proportional to the frequency of light, as described by the equation E(un), where E is the energy of the photon, h is Planck's constant, and nu is the frequency of light. But here's the catch. While photons behave like particles, they are massless. Yes, you heard it right. These particles of light, zipping around at the speed of light, carry energy and momentum, but have zero rest mass. So we see that light, in its enigmatic existence, behaves both as a wave and as a particle. But how does this relate to the electromagnetic field? Let's delve into that. You might be familiar with the term electromagnetic field, but what does it really mean? Let's delve into a world unseen by the naked eye, a world of fields and waves, of energy and motion. The electromagnetic field is a fundamental concept in physics, a field of force produced by electric charge and motion. It permeates our universe, influencing the behavior of charged particles. It's composed of two interrelated aspects, the electric field and the magnetic field. These fields oscillate in harmony, creating waves that propagate through space at the speed of light. But it's not just about waves. The electromagnetic field has a dual nature. Just as light can behave as both a wave and a particle, so does the electromagnetic field. Here's where the concept of photons come into play. Photons are the particles of the electromagnetic field, massless carriers of energy and momentum. And this brings us to a fascinating concept, the quantization of the electromagnetic field. This means that the electromagnetic field isn't a continuous flow of energy, but rather, it consists of discrete packets or quanta. These quanta are our aforementioned photons. Each photon carries a specific amount of energy, determined by the frequency of the electromagnetic wave. This is represented by the equation E(un), where E is the energy of the photon, h is the Planck constant, and nu is the frequency of the wave. This idea of quantization, first introduced by Max Planck and further developed by Albert Einstein, revolutionized our understanding of the electromagnetic field. It was a departure from classical physics, which viewed the electromagnetic field as a smooth, continuous entity. The quantization of the electromagnetic field has profound implications. It's the reason why we can talk about light particles, why we can study the interactions of light with matter at the microscopic level, and why we can harness the power of light in technologies like lasers and solar cells. Now we understand that the electromagnetic field is not just a continuous flow, but consists of discrete energy parcels, or photons. But how does this quantization occur? For that, we turn to the work of some brilliant minds. Albert Einstein, a household name, provided a crucial piece of the puzzle. His explanation for the photoelectric effect introduced a revolutionary concept. In the early 20th century, Einstein was grappling with the mysteries of light. He was fascinated by the idea that light could behave as both a wave and a particle. In this quest, he stumbled upon the photoelectric effect. This effect, simply put, is the emission of electrons when light is shown onto a material. What was intriguing about this effect was that the energy of the emitted electrons did not depend on the intensity of the light, but on its frequency. This was a puzzle for scientists of the day, who believed light to be a wave. By all accounts, the energy of the emitted electrons should have increased with the intensity of light. Enter Albert Einstein. In 1905, he proposed a radical idea. He suggested that light was not just a wave, but also consisted of discrete packets of energy. He called these packets quanta. Each quantum of light, or photon, had an energy proportional to its frequency. The proportionality constant was none other than the Planck's constant. Einstein's theory elegantly explained the photoelectric effect. The energy of the emitted electrons was determined by the energy of the individual photons, not the overall intensity of light. Einstein's proposal was a groundbreaking departure from classical physics. It introduced the notion of quantization, the idea that certain physical properties come in discrete amounts. This concept would later become a cornerstone of quantum mechanics. But the story doesn't end here. Einstein's work laid the foundation for the concept of quantization. But it was another scientist who wove this concept into the fabric of the new quantum mechanics. Paul Dirac, a less well-known but equally important figure, took Einstein's idea of quanta and applied it to the electromagnetic field. This is known as second quantization. A brilliant mind in the realm of quantum mechanics, Dirac made a monumental leap by integrating the concept of photons into the framework of quantum mechanics. But what exactly did he do? Dirac took the phases of different electromagnetic modes and their energies and decided to quantize them. To put it simply, he reimagined them as operators and proposed commutation relations between them. Now, you might ask, what is quantization? In the simplest terms, quantization is the process of transitioning from a classical understanding of physical phenomena to a quantum one. It's like moving from viewing a film strip as a continuous flow of images to realizing it's actually composed of discrete frames. In the case of Dirac's second quantization, the Fourier components of the electromagnetic field were quantized. Fourier components, in essence, are mathematical tools that allow us to break down complex waveforms into simpler parts, much like decomposing a symphony into individual notes. Dirac's quantization of these components led to a profound realization. The electromagnetic field could be understood as a collection of discrete energy packets, which he called photons. These photons, as Einstein had previously proposed, were particles of definite energy, momentum, and spin. But Dirac didn't just stop at quantizing the field, he delved deeper. He introduced a quantum mechanical photon state, a concept that further detailed the properties of the photons in the electromagnetic field. This quantum mechanical photon state was characterized by a specific mode, which in turn defined the photon's energy, momentum, and spin. Dirac's second quantization gave us a way to understand the electromagnetic field as a collection of discrete energy packets, or photons. But what are the properties of these photons? Photons, the discrete energy parcels in an electromagnetic field, possess some fascinating properties. These massless particles are the embodiment of light and electromagnetic radiation, carrying energy across the universe at the speed of light. But how do they come to possess these properties? To answer this question, we delve into the quantization of the electromagnetic field. This concept, introduced by Paul Dirac, posits that the electromagnetic field is composed of discrete energy parcels, the photons. Each photon is characterized by its energy, momentum, and spin. A photon's energy, represented as Hn, is determined by its frequency, denoted by nu, and the Planck constant, h. The Planck constant, a fundamental constant of nature, is the bridge between the world of classical physics and the quantum realm. It helps us understand that energy is not continuous, but quantized, broken up into little packets, photons. Next, let's talk about a photon's momentum. Remember that momentum is typically the product of mass and velocity. However, photons, which are massless, still carry momentum. How is this possible? This momentum, represented as hk, is derived from the wave vector, k, and the reduced Planck constant, h. It's a fascinating twist that only occurs in the quantum world. Finally, we come to spin. Photons possess a definite spin, with the eigenvalue of the z component being 1. This property is attributed to the polarization of the photon, another unique aspect of these intriguing particles. By quantizing the electromagnetic field, Dirac was able to incorporate these properties into the photon concept. This quantization, which transformed classical fields into quantum operators, marked a significant advancement in our understanding of light and particles. Understanding the properties of photons and the quantization of the electromagnetic field brings us closer to unraveling the mysteries of light and particles. As we continue to explore these concepts, we open doors to new technologies and insights into the fundamental nature of the universe.